All right. Again, as I mentioned last time, hackathon team's already out. So if you were not already in contact with your team, make that happen. Email your team leads email your teams, blah, blah, blah. You guys should already be discussing app ideas for Saturday. If you want, you can start creating, graphics or something like that if that's a benefit to you guys. If you're not signed up for the hackathon, I would highly encourage you to start working on the penalty assignment yesterday, because it is a monster. 12-page paper.
Really?
Oh yeah, it's up on. You can go read all about it. It's up on Blackboard. So if you go to the hackathon, all you have to do is submit a picture of yourself at the hackathon instead of a 12-page paper. If you don't go to the hackathon, you got a monster of an assignment. A monster of assignment. It's a good assignment. I think it would be a good paper to write, but it is a monster. Okay, so let's talk about recursion. All right, so recursion is when a function is defined in terms of itself. All right, or if we want to put this a different way, we could say it is a function that makes a call to itself from within itself. All right, that's the high-level description of what recursion is. Now let's look at recursion through a real-life example. All right, so if we look at the factorial problem. So for instance, 4 factorial is equal to 4 times 3 times 2 times 1, right, which is 24. Mm-hmm. So if we were solving the problem for 4 factorial, we get a 24. Now, we can go ahead and we can write this. So I'm going to go and we're going to write this iteratively. So go into Atom here. And I'll just define a function up top here. So we're going to call this guy factorial. It's going to take in a number. And we're going to count down. Well, we can also count up. But we'll go ahead and count down from that number all the way down to 1. Okay? So, and we're going to create a answer. We'll start this guy equal to 1. We'll say for I in range. And we're going to start at num and go all the way down to, if we're going to be official about this, we go all the way down to and including a 1. So I'm going to go to 0, step by -1, even though anything times 1 would be that anything, so you technically would not have to go all the way down to 1. You could go all the way down to 2. But we'll go all the way down to 1. And we'll step by -1. So this will go, for example, if this was 4, this would start at 4, then go to 3, then go to 2, then go to 1. Mm-hmm. Each time through, we're going to say answer is equal to answer multiplied by the current value of I. When all is said and done, we'll return answer. So that is an iterative version of factorial. If we want to see this guy run, we'll just come down here. We'll go ahead and print out the factorial of 4. I'll dump this other stuff. Let me run this real quick, and then we'll walk through the code again. Desktop. All right, so there's our 24 for calculating the factorial of 4. If I instead wanted to do the factorial of 5, that should give me a 120. There's my 120. Scroll back up. There's our iterative version of factorial. So if I passed in a 4, answer, we start off as a 1. That way we can get the ball rolling with the thing. We could also start answer off at num if we wanted to, and then count down from num minus 1 to 1. That would do the same thing. So if we passed in a 4, answer would start off as a 4. The first time we'd multiply it by a 3, then a 2, then a 1. All right, ultimately, same logic. Still have our 120. All right, so questions about the iterative version of Factorial. And what I mean by iterative, I mean using a loop. Okay, we're using a loop to write this guy. We're iterating over a loop multiple times.
I have actually kind of a separate question.
Sure.
I noticed you have semicolons in there, and it worked fine. Yeah, that's probably just because of C.
Oh, yeah.
But it functioned fine, which I was concerned.
It just ignored it. But yeah, that was a problem. You don't want to put semicolons in here.
Okay.
Yeah, that's C#. That's how you end lines in pretty much every other language except Python. All right, so now if we go back and think about factorial, and we think about 4 factorial. 4 factorial is actually equal to 4 times 3 factorial, is it not? Because isn't 3 factorial 3 times 2 times 1? So actually 4 factorial is 4 times what effectively is 3 factorial. 3 factorial is equal to 3 times 2 factorial. 2 factorial is equal to 2 times 1 factorial. And 1 factorial is equal to 1. That make sense? Mm-hmm. So that's another way of thinking about factorial in terms of factorial itself. So I calculate 4 factorial by multiplying 4 times whatever 3 factorial is. 3 factorial is 3 times whatever 2 factorial is, so on and so forth. So if we're going to write the recursive version of this guy, we'll call this guy factrec for factorial recursion. We'll take in a number. We'll ask the question, if num is equal to 1, we'll return 1. Otherwise, return num times factrec of num minus 1.
Oh. Okay.
All right, scroll down here real quick. We'll print factrec of 5. We should get the exact same output. So there's factrec of 5. And this is the recursive version of this. So for instance, if I were to pass in a 4 for num, is 4 equal to 1? It is not. So we drop past this if statement and we get to here. We can put an else in here if you prefer the way that looks. That'll do the exact same thing. But a return statement makes a function immediately end, which means that when I had return outside of the if statement here, the only way I even ever get to this line is if I survived this. Make sense? It's almost like a minefield type thing. All right, so assuming num is 4, we ask the question, is 4 equal to a 1? No. Those are different numbers, right? 4 is not a 1. So we will not get into the body of the if statement. Instead, we'll come down here, and what we're going to do is we're going to return whatever num is, which is 4, multiplied by whatever factrec returns for a 3. We have to wait for that, right? Factrec's not going to be done for a 3 yet, so this guy's kind of put on hold, paused. So if we go back here, what just happened, let's kick it to, let's just give myself another slide here. We'll call this guy factrec. So factrec of 4 would be equal to 4 times factrec of 3. So we don't get an answer to this guy yet until we have an answer from this guy. All right, so this version, the version where num is equal to 4, is put on hold. And now we have another call to factrec where we're trying to calculate the factrec of 3. Is 3 equal to 1? Nope, still different numbers. So we'll return 3 times the factrec of 2. Now we have to wait again because factrec of 2 needs to return before we can get our answer here. So now we have another call to factrec where num is equal to 2 because we're saying return 3 times the factrec of 2. Factrec of 2 is 2 equal to 1? Nope, they're different numbers, so we'll return 2 times the factrec of 1. All right, now we have to wait on the factrec of 1. So we pause this version where num is equal to 2, spin back up, passing in 1 for factrec. Is 1 equal to 1? It is. So we immediately return 1. Done. No more factorial calls. So this guy becomes a 1, which then allows us to get the answer for this guy, which gives us a 2, which then allows us to get the answer for this guy, which then gives us a 6, which then allows us to get the answer for this guy, which is a 24. And that's our original call to factrec. Makes sense how it worked? Mm-hmm. All right. So one challenge you're going to have for a while is that recursion is difficult to conceptualize in your head. When you go to solve problems recursively, it's going to be tough for you. Now, what's funny is when you take the 470 class, so as either a junior or a senior, depending on when that class is offered in your, because it's only offered every 2 years. In that class, we use a language called Scheme to write our own programming language, and that language does not support loops. So you have to write everything recursively. Now, in effect, if you kind of throw this idea of recursion out, and we went through this, we kind of just built a loop, right? Mm-hmm. We were spinning back up and going to the next iteration, then doing some more logic, then spinning back up. We just kind of invented our own loop by calling the same function over and over again, rather than having a little loop structure in there that spun through. All right. Now, having said that, it's not the same thing as a loop. In fact, we would usually say that recursion is memory inefficient. But often leads to elegant solutions. So you can usually get these solutions that almost look magical in nature. When you see it, sometimes you'll have you could write a whole bunch of code that does something complex. And if you can conceptualize that problem recursively, and not all problems can be done recursively, but if you can conceptualize it recursively, a lot of times the solution tends to be a lot smaller, a lot shorter. Now, our end-all goal as a programmer is not to write short code. Right? That doesn't make us a better programmer if we did something in 3 lines rather than 7 lines. Okay? You'll be your best programmer if you write accurate code regardless of how many lines it is. Make sense? So don't strive to minimize the number of lines to the point where it no longer makes sense, because that is something that happens with recursive solutions sometimes. If somebody writes, there's this website called topcoder.com, which is kind of an online programming competition website. You can make real money off of it and stuff like that. It's kind of cool. I used to do a programming team here, and then not a lot of people were interested in it. So if you're ever interested in that, we can look at it again. But in any case, years ago, one of the top players, because the way it would work is every week there would be like a tournament, and it's all online. You didn't have to go somewhere, and you got put into some random room with like 4 other people, and you would have an hour and they gave you 3 problems. There was like an easy problem, a medium problem, and a more difficult problem. And the number of points you got for a problem was depended on how long it took you to write it and then submit the code for that problem. Then later on, they would determine whether you got those points, whether your solution worked. And there was after the hour was up and everybody had their code submitted, there was then a 15-minute period where you could go and look at other people's code that was in the same room as you and try to break it, try to find things that were wrong with it, and you would get points, beneficial points for debugging their code. They would lose all their points because their solution doesn't work, but you would get points for finding a solution that doesn't work, that kind of thing. And then in the end, it would run it through their system test where it would test your code thoroughly against 1,000 inputs or something, and either say it worked or it didn't work, whether you passed all the tests, and you finally get your points, and the number of points you get makes your ranking either go up or go down. So there's one guy, he was the number 1 ranked top coder guy in the world. And he was a PhD student in combinatorial mathematics. We don't have that class here. I took combinatorics when I was in school. It was a required course for computer science, and it's complex math. It was a difficult math class, and I don't remember most of it. But in any case, this guy was effectively an expert at combinatorial mathematics. He knew all the little math tricks. You couldn't read half this guy's solutions because they were all based on these like math patterns that like most people would not have known. So you would have one person who had a solution to a problem that was like 100 lines long, and then you have this guy. His was like 9 lines long for the same problem. It was amazing. It was pretty funny. But, in any case, so he was actually playing defense, right? He was writing his code quickly because he didn't have to write very much stuff. He was writing his code almost like in encrypted format because it was really hard to follow because you didn't know what math tricks he was using under the hood. But then at the same time, you really couldn't debug his code. So he was defending against other people getting extra points off of his code. So kind of an interesting thing. But in any case, all of you should mentally prepare yourself for not being very good at recursion for a while. And the reason I brought up the 470 class, and this is kind of an interesting observation that I've made for years and years and years now, students come into 470 intimidated by recursion. All right, so keep in mind, that's 2 years from now, you're still going to be intimidated by recursion. So that's where you're going to be, and that's okay. Eventually, we're rewiring our minds here to the point where we'll no longer be able to communicate with normal humans. So, in any case, they go into this class. Now they're forced to deal with this language that doesn't support loops. So they have to write every problem recursively, effectively replacing whenever they would use a loop with a recursive call. So they come out of that class being very, very good at recursion, to the point where they then have to retrain themselves to think iteratively because they want to solve every problem recursively when they leave that class. It's kind of an interesting thing that comes out of that. Okay, so questions about how recursion works at this point. We conceptually understand that recursion is what a function calls itself from within itself. Okay, and we were intimidated that can we ever come up with that solution on our own? All right, so now, last time we wrote an insertion sort, correct? Mm-hmm. All right, and that's kind of, we're going to call that a slow sort. It works, it's a functional sort, but in the big scheme of things, it's not a very fast sorting algorithm. At some point, we'll maybe come back. I think does the book talk about big O notation? Well, whatever. I don't want to talk about that today because we don't have time. But it talks about the efficiency of an algorithm. And one of the things we can do is we can, say that something has a big O value of n squared, where, really it comes down to how many questions do we ask as we go through there. And the more questions you ask, the more inefficient an algorithm is. Okay. Something along those lines. I'm kind of the opinion that big O value kind of goes out the window. Like complexity of an algorithm isn't as important today as it used to be when you consider that we have multi-core processors, and even you can have your programs running on multiple machines that each have multi-core processors. So this idea of how long it takes something to run on a single core CPU really isn't the normal thing, the normal way programs run anymore anyways. That doesn't mean it's not conceptually important from a computer science theory perspective. I'm just not sure how useful it is today. So what we're going to look at today is a sorting algorithm called merge sort. And merge sort's very interesting, kind of along the lines of what I just mentioned. So we would say merge sort would be incredibly slow if we were running on a single computer running a single processor, single core. But it's among the fastest sorting algorithms that can exist if we either have a lot of cores or we're running it across a bunch of machines. All right, so we're going to talk about how merge sort works. So let's give ourselves, here, I'm going to steal my stuff from here. And then we gotta shuffle this up, right? All right. So you're going to want to take good notes on this because you will be writing a merge sort for Friday. And it is not going to be fun. But when you see the solution, you'll also notice that the solution is not long. So there's not going to be that many lines that go into the solution, but it's going to cause you to think. All right, so first thing we look at is we look at we have this list that we want to sort. We ask ourselves, from a computer's perspective, is that list sorted? Now, as humans, we immediately say no, that's not sorted, right? And then I would say, well, how do you know it's not sorted? You say, well, I just looked at it. Right off the bat, the 7 is greater than the 1. This guy's out of order, not sorted. But from a computer's perspective, if we're asking the computer to, at a glance, determine whether this list is trivially sorted or not, we're going to say it is not sorted because it's not a 1 list. A list that only contains 1 element is by definition sorted, correct? If I gave you 1 number and I asked you, is this sorted? You would say, yeah. You didn't even have to look at the number. You could do that blindfolded, right? You hold 1 number in your hand, and I'm asking you, here's a collection of 1 numbers. Okay, you're blindfolded. I ask you, is that sorted? Yes. You don't have to know what that number is. It's sorted. Make sense? All right, so merge sort operates off of that concept. Is something trivially sorted? So we're going to ask ourselves, is this 5 list trivially sorted? We're going to say no, because it's not a 1 list. So since it's not a 1 list, what are we going to do? We are going to divide the list in half and then call merge sort on the first half and call merge sort on the second half. All right, so we made our first call to merge sort. Let's call it MS up here. On that whole list. We decided that guy is not the 1 list, so now we're going to call merge sort. Now, it doesn't matter whether you divide it in half with the larger half on the left or the larger half on the right, as long as you always divide it the same way. All right, so we're going to assume that the way we'll divide it, so will always be the larger half will be on the left. So that is taking the I'm going to have you come up with the math for that. But effectively, we're dividing it in half. So that's actually kind of fun math to come up with. One thing you'll find is if I'm working on the left-hand side of this list, the middle is going to be 4 minus 0 divided by 2. 4 minus 0 divided by 2, so that's the middle point. Make sense? So we can say everything from that point is the left half. And then everything from that point plus 1 to the end is the right half. So we're going to call merge sort on this left half. We're also going to call merge sort on the right half. So when we decided that this original call to merge sort is not trivially sorted, we split our data in half and we call merge sort on the left and we call merge sort on the right. Assuming this is our second call to merge sort, if it's in our program, we call merge sort, then we call merge sort again right underneath that. We don't get to that second call until that first call has completely finished. And you're going to see that work here. So this guy has not even executed yet. We're working on the first call to merge sort. So we're going to ask ourselves, is this sorted? No, it's not a one list. So we're going to split this guy in half. We'll call merge sort on the left. We'll call merge sort on the right. Give myself a little bit more vertical space here. All right. Should probably do it even. I think we'll be good. All right. So then, again, this is the first call. This call has not even happened yet. It's still on hold. So we're still waiting to return from this call up here. So this guy has not happened yet. So the only merge sort calls that we're currently executing is we're currently executing this one, which has now paused to wait for this guy to return, which has now paused to wait for this guy to return. So we ask ourselves, is this list sorted? It's not a one list. So we call merge sort on the left half. We call merge sort on the right half. Okay, now this guy right here, this call to merge sort, is waiting for this guy to finish. Is this guy sorted?
Yes.
It is. This is that example of you being blindfolded and I hand you one number. This is sorted, so this guy just immediately ends. So now this call to merge sort has finally finished the call to his left-hand side, so now he can make the call to his right-hand side. Is that guy sorted?
Yes.
He is. So that guy returns. So now from this guy's perspective, what he has is he has a left half of the list and a right half of the list that are in and of themselves sorted. So his left half is in order. His right half is in order. Now what he needs to do is merge those two halves together so that his version, his portion of the list is sorted. So he's going to go ahead and make an empty list of the same size as he currently has. I'll kind of put this over here to the side here so you can see the merge algorithm. So he's going to make an empty list that's of the same size here as our portion of the list. So we have a 2 list here that this guy cares about. We have a 2 list here that this guy is going to try to fill in. So what we're going to do is we're going to create 2 variables. Well, let's call this pause 1. And pause 2. And we're going to say that these guys, pause 1 points to the beginning of the left half of the list. Pause 2 points to the beginning of the right half of the list. All right. Now we know that the left half of the list is already sorted. We know that the right half of the list is already sorted. Now in our example here, that isn't all that impressive, right? Because both of those guys are one list, but you're going to see how this unfolds here in a second. All right. So now we ask ourselves, which is smaller, the value that lives at pause 1 or the value that lives at pause 2? Pause 2. So we're going to declare that guy as the winner. We'll put him in our first place here. And then we're going to increment pause 2. So now pause 2 points off the end of your portion of the list. So then we ask the question again, which is smaller, the value at position pause 1 or an illegal position? And the value at position pause 1 is smaller because an illegal position can't be used. So we're going to say that the 7 is the winner. And this guy then walks off the end of his portion of the list. Now we knew we had to go through this exactly 2 times in order to get our list sorted. Now, so that was the merge step we just did. Now we need to copy these values back in over our originals. This is a 1. This is a 7. Now remember, when we're dealing with lists, we have a pointer to the original. So when I made a 1 and 7 here, when I changed those values, what happened to this 1 and 7? They changed. They changed. Because these guys point to the exact same place in memory, like we talked about last time. All right, so I gave myself a little temporary list here to do my merge step in. But then I copied the contents of that temporary list back into the original list in the portion of the list that we care about. And that'll make sense when we get to the right half of the list, that we're dealing with buckets 3 and 4 of this larger list. So we need to make sure we copy them back into the right places. So when I overwrite the original list with the 1 and 7 here, all the other things that point to that list will also see those changes. All right, so we are done with the merge step here. So therefore, that call to merge sort is done. This guy was waiting for his left call to merge sort to finish. Now it's finished. So what does he do after the left? He sorts the left-hand side, calls merge sort on the right-hand side. Is this guy sorted? He is. So that guy can immediately return. We don't need to do a merge step for a 1 list. He immediately returns. Then we do our merge step. We make pos 1 point at the beginning of the left half of the list. We make pos 2 point at the beginning of the right half of the list. We give ourselves a temporary array that's of the same size as the portion of the list that we're working with. And what I'm going to do here, I'm going to go ahead and add another variable in here that we would have used last time too. This will be beneficial when you get to the right-hand side. So we're going to call this index. You can call it whatever you want, but when we are picking a winner from our actual list, we're going to be putting in bucket 0 of our temp list, or then bucket 1, then bucket 2. But we might be operating off of bucket 3 and 4 in the original list. So we have to keep track of where we are in these different lists. So pos 1 points at bucket 0, pos 2 points at bucket 2, because bucket 0 here is the beginning of the left half of my list. Pos 2 points to the beginning of the right half of the list in this portion of our list that we're looking at. So then we ask the question, who wins between a 1 and a 5? Who's smaller?
The 1.
A 1. So we'll place the 1 at position index, increment index. Since pos 1, 1, increment pos 1. Which is smaller, the value at pos 1 or the value at pos 2? 5 is smaller than a 7. So we'll place the 5. We'll increment index. And since pos 2, 1, we'll increment pos 2. Who wins, the value at pos 1 or an illegal position? Value at pos 1. Illegal positions are not usable. So we'll take the 7, store them at bucket index. We would go ahead and increment index even though we know we're done. Since pos 1, 1, we would increment pos 1. Now both of these guys point off the ends of their respected lists, right? Pos 1 no longer points to a position in the left half of the list. Pos 2 no longer points to the position in the right half of the list. Now, they might point to a position in the list. So technically right now, pos 2 is actually pointing right here to bucket 3, which is a legal place in our list, but not part of the list that this call to merge sort cares about. Make sense? All right. So we know we are only going to have to do comparisons, in this case, 3 times. Because that's how big our list is. So once we have our list here, our sorted list, we copy it back over. There's a 1, there's a 5, there's a 7. So we'll go through every bucket of this, copy it into the equivalent buckets of the equivalent positions in our real list. So 1, 5, 7 changes there. which then also means it changed here automatically. We don't have to do anything special because we're changing it in actual memory. And now this call to merge sort has ended. This guy was waiting for the left half to finish. So now he can finally call his merge sort on the right half. Is this list sorted?
No.
Nope. So we're going to call merge sort. Now this is where you're going to want to pay extra attention because now we see when we're on the right half of the list, even though we're dealing with bucket 0, 1, 2, things like that over here, we're actually dealing with positions 3 and 4 in our list here.
Okay.
All right, so I'll explain as we kind of get in there, but that's where you want to make sure you're keeping track. That's why we have 3 variables here. That's why index points to where we are in our temp array, and pos 1 and pos 2 point to where we are in the real list.
Okay.
So we're going to call merge sort on the left half, and we'll call merge sort on the right half. All right, now this call does not happen yet because this call to merge sort is waiting for this guy to return. Is this guy sorted? Yep, so we're done. We don't have to do any merging. I mean, we could waste our time merging. One list is sorted. We don't need to do anything. So that guy's done, which then allows us to finally make our merge sort call on the right half. Is this guy sorted? Yep. So we delete, well, that call to merge sort's done. So now we have finished our 2 calls to merge sort from this guy. And what do we do after we've called merge sort twice?
We have to go to a temporary.
We have to do the merge step. Yep. Because we know that the left half is sorted and the right half is sorted. Make sense? All right, so we'll go ahead and give myself a temporary array of the same size as those guys, and I'll go ahead and, well, I'll put it over here. All right, but now this is a brand new array that I just created. So it's going to have a bucket 0 and a bucket 1. Right? I just created an array of size 2 to hold 2 elements. Yet, the positions in my real array is bucket 3 and bucket 4. Okay, so you'll see the catch here in a second. So we're going to go through every bucket of this guy and compare pos 1 and pos 2 in this guy. So who should come first, a 4 or a 2? 2. So we'll put the 2, which lives at bucket 4, lives at bucket pos 2, we'll place it in bucket 0 of this guy, bucket index. We increment index. We increment pos 2 because he was the winner. Which should come first, a 4 or an illegal position? 4. So we'll place the 4. Increment index. We know we're done now. Increment pos 1. So technically, pos 1 is pointing to a real place in the list, but we're done. This is an illegal position from the perspective of the left half of the list. Those are the only legal buckets. This is an illegal position from the perspective of the right half of the list, because these are the only legal buckets. And we filled up our temporary array. So all sorts of things that tell us that we are done doing the work for right now. Okay, so this is the part that we need to be careful of. It was trivial before because of how we were copying it back. So I want to overwrite my little portion of the array here, my little portion of the list. That means I want to overwrite bucket 3 with what lives at bucket 0 here. And I want to overwrite bucket 4 with what lives at bucket 1 here. Now, up to this point, I've been mentioning we're keeping track of the, which portion of the list we care about. So all along, we've probably had 2 other variables in here. Maybe called begin and end. So begin and end, they don't change. When we call merge sort on the right half, we're calling merge sort, passing it the original list and passing it the beginning of the portion of the list it cares about and the ending of the portion of the list it cares about. So we're saying, here's the entire list. So this version of merge sort actually gets the whole list. But then he gets two little integers that say, I want you to focus on bucket 3 to bucket 4. That's the portion of the list that you're in charge of. That make sense? And those values don't change. That's just keeping track of what portion of the list we care about. So when we copy stuff back from here, we're going to be going from bucket 0 to 1 to 2, however many buckets this is. And we're going to be copying it into bucket 3 or 4, so on and so forth. So starting at bucket begin, going all the way up to and including bucket end, we're going to copy 0 and then 1. All right, so we're going to copy the 0 into bucket begin. We'll copy the 4 into button begin plus 1, begin plus 2, plus 3, so on and so forth. All right, so we make the change here, 2 and 4. That makes the change permanent here. So this call to merge sort is now done. And I'll go ahead and show you the original call to merge sort. Begin was 0. End was 4. So when we originally called merge sort, we told it the portion of the list you care about is the whole list. Bucket 0 all the way up to and including bucket 4. So we had two integers that kept track of where we were in the list. All right. So now we've split this guy a bunch of times. The left half is sorted in and of itself. The right half is sorted in and of itself. So now we do our merge step. We give ourselves a temporary array. We make, here, let me move this out of the way a little bit more. I'll go ahead and make begin and end, point back to the beginning and ending of this guy. We'll make pause 1 point to the beginning of the left half. We'll make pause 2 point to the beginning of the right half. So pause 2 is legal as long as it's less than or equal to end. Pause 1 is legal as long as less than we would probably keep track of where the end of these guys list, but we would say as long as it's less than in this case less than or equal to begin plus end divided by 2, which is 2. So that's the legal endpoint of our left half. So we're going to ask the question, which comes first? A 1, so position pause 1, or position pause 2? A 1 or a 2?
1.
A 1. So we'll put that at bucket index. Increment index, since pause 1, 1, we'll increment that guy. Which comes first, a 5 or a 2?
A 2.
2. Increment index. Since pause 2, 1, we'll increment pause 2. Which comes first, a 5 or a 4?
4.
4. Put that at bucket index. Increment index. Since the 4, 1, increment pause 2. Which comes first, a 5 or an illegal position? 5. Increment index. Increment pause 1, because it won. Which comes first, a 7 or an illegal position? 7. Increment index, so we know we're done. Increment pause 2, or pause 1 rather, since that guy won. Then we go through and we copy our temp array back over. So this is a 1, a 2, a 4, a 5, and a 7. So that's the result after our final merge step on the left and right half of our list. And now our list is sorted. That make sense? All right. So it looks pretty easy.
That's brutal.
It won't be as bad as you think. I'm going to get you started a little bit here.
Okay.
So we're going to have a def merge sort. And this guy's going to take a list as a parameter. And I'm going to create another function here called ms. Maybe we call this guy merge sort helper. This guy's going to take a list, a begin, and an end. All right. So this merge sort helper, this guy takes in the entire list and also takes in where does his portion of the list begin and where does his portion of the list end. So in merge sort, we're going to ask the question, if length of LST is greater than 1, it is not sorted, right? Therefore, we're going to go ahead and call ms helper twice. We're going to call it on the left half of the list, which would be 0. So here, I will do this. We're going to do begin 1 is equal to 0. End 1 is equal to end plus begin divided by 2. And then begin 2 is equal to end 1 plus 1. End 2 is equal to, in this case, the length of list minus 1, the last legal position in our list. So then we're going to call merge sort helper, passing it the list, passing it begin 1, passing it end 1, and call merge sort helper, passing it the list, passing it begin 2 and end 2. All right, this is all merge sort will ever do. It's merge sort helper that does all that work. Okay? Because this guy is going to get the whole list as well as the portion of the list he cares about. That make sense? So this guy's going to check if one list. If so, return. Otherwise, call merge sort. I'll call ms helper on left half. Call ms helper on right half. Perform merge step. That's what ms helper would do. And when it all is said and done, you'll be able to go back out here and you'll be able to say print my list beforehand. Then you'll call merge sort on my list. And then you'll print my list again, and it should be sorted. I'll just leave all that in there, I guess. Make sense what we're doing? All right. Make sure you work with your group on this. I know we have the study group going, or we have a couple study groups going. I think that'll be helpful. It's not as hard as it looks. We're keeping track of 5 integers in a list. So we're getting used to kind of juggling lots of variables. All right. I will see everybody on Friday. I'll go ahead and post this code up on Slack so you have access to this as a starting point. Huh? Due Friday.